Now we will take a look at the reduction of carbonyl groups in ketones and aldehydes. Some of the reactions are the ones we've learned before. The first one is the hydride reduction. The reagent is sodium borohydride or lithium aluminum hydride. And we've learned that aldehyde can be reduced to primary alcohols, and the ketones can be reduced to secondary alcohols. The difference between sodium borohydride and lithium aluminum hydride is that lithium aluminum hydride is more reactive. So lithium aluminum hydride can reduce not only aldehydes and ketones, but also carboxylic acids derivatives. Sodium borohydride can only reduce ketones and aldehydes, not carboxylic acid derivatives. All right. Previously, we didn't talk about the mechanism. The first step is the nucleophilic addition reaction that we have been talking about in this chapter. Sodium borohydride, the hydride reducing agent, they have the hydrides available, H with the negative charge, so that could serve as the nucleophile, even though you will not see H minus as a free ion, but you can think of it that way. It's the hydride that attacks on the carbonyl carbon. Hydride is the reducing agent, or is the nucleophile. So the CO double bond breaks, and instead of having O minus, the O will attack on boron, making an oxygen-boron bond. So that's the intermediate forms. And remember, there are 4 equivalent of hydrides attached to boron. All of them can be used to reduce the carbonyl. So 1 equivalent of sodium borohydride can actually react with 4 equivalent of a carbonyl compound. So suppose we have a second equivalent of the carbonyl, the ketone. So the second hydride can be transferred to the ketone carbonyl. And now we have 2 of this OR group attached to boron. The same reaction will be repeated twice. Eventually, all the hydride will be delivered to the carbonyl carbon, and there will be 4 equivalent of the OR group attached to the boron. And we call this the borate. Then it will be the hydrolysis of the borate. So water will attack on the boron and break the OB bond. So the oxygen from the alkoxy group will take a proton from the solution to become alcohols. This step will be repeated 4 times total. So 4 equivalent of the alcohol will be released from boron, and we got this boronic acid as the byproduct. Okay, so that's the mechanism. It's actually pretty straightforward. You may have difficult understanding why we have 4 equivalent reacting. If that's the case, I think what you need to know is only that hydride from boron can be delivered to the carbonyl carbon. That's it. And you know 1 equivalent of sodium borohydride can react with 4 equivalent of the carbonyl. And that should be sufficient. All right. So the key step is the first step, nucleophilic addition by the hydride. Anyway, in the reduction, we have added 2 hydrogen atoms across the CO double bond. These 2 hydrogens have different source. The hydrogen goes to the carbon is from the hydride reducing agent, while the hydrogen attached to the oxygen is from water. It's added during the workup stage. So if we use deuterium, the isotope of hydrogen, to label any of the hydrogen used in the reaction, it's easy to differentiate, or it's easy to track the source of the hydrogens. For example, in the first reaction, we have D in sodium borohydride. So this D will end up on the carbon, while the H from water, H2O, goes to the oxygen. In the second example here, we have H in sodium borohydride, but D in D2O. So the H goes to the carbon and the D goes to the oxygen. It becomes OD. The second reduction reaction is catalytical hydrogenation, and it gives the same results as hydride reducing agent. Aldehydes to primary alcohol, ketones to secondary alcohol. Okay, very straightforward. But one thing I do want to point out is that catalytical hydrogenation can reduce CC double bond and CO double bond at the same time. But lithium aluminum hydride and sodium borohydride, the hydride reducing agent, can only reduce CO double bond, not CC double bond. Okay, so that's the difference between these 2 reactions. The third reduction is called reductive amination. Amination means introducing an amino group. The reaction has 2 steps. The first step is the one that we have talked about not long ago, the imine formation. Reaction between a carbonyl with a primary amine. So it forms an imine with carbon-nitrogen double bond. The second step is the reduction. It's going to reduce the CN double bond to CN single bond. So the product will be an amine. So imine is reduced to an amine. The reducing agent here could be the hydride reducing agent that we have talked about before, sodium borohydride, lithium aluminum hydride. But later, they have discovered one reducing agent that works better, in which one hydride has been replaced by cyanide. So it's the sodium borohydride cyanide. Okay, so this reducing agent works best for reduction of imine to amine. Now, as I said, this is a very important reaction to introduce an amino group or a substituted amino group to the system. And when we move on to the amines in chapter 23, we will revisit this reaction. The last reduction we will look at is the reduction to hydrocarbons, which means we can reduce the CO double bond to CH2, a methylene group. So the oxygen can be removed completely. There are two reactions or two reagents that can do this. The first one is called Clemmensen reduction, and it uses the zinc and mercury in concentrated HCl to do the reduction. The second reaction is called Wolff-Kishner reduction. The reducing agent is hydrazine, NH2NH2, with KOH, potassium hydroxide, and it typically takes place in diethylene glycol, which is a high boiling point solvent. All right, so both of these two reaction conditions could convert CO double bond to CH2. The difference between them, Clemmensen reduction is under acidic condition. It uses HCl, while Wolff-Kishner reduction is under basic condition. It uses KOH. So let's take a look at a couple examples. Say we have cyclohexanol and we reduce it with zinc mercury and HCl. So the product will be cyclohexane. The oxygen is removed completely. All right. And to do this reduction, we can also use the Wolff-Kishner reduction, right? It will not have any difference. The next example will show the difference between Clemmensen reduction and Wolff-Kishner reduction. So suppose, okay, so here we have an aldehyde functional group, and we also have an acetal, which is a protected carbonyl, right? Suppose we only want to reduce the aldehyde to CH2. What reagent should you choose? You can use only one, not the other. In this case, you want to choose the Wolff-Kishner reduction because Wolff-Kishner reduction is under basic condition. The acetal protecting group is stable under basic condition, and it will not be touched. So only the aldehyde will be reduced. If we do the reaction Clemmensen reduction under acidic condition, the acetal protecting group could be hydrolyzed, right? Acetal can be hydrolyzed under acidic condition. So it's hydrolyzed, and it's going to give a ketone in this case. And under this reductive condition, the ketone carbonyl can be reduced as well. So for Clemmensen reduction condition, the final product we will get will be hexane. Okay, so you see the difference? Since we have an acid-sensitive group in our starting material, and we don't want that to be touched, then we need to pick the basic reduction condition. If the acidic condition is picked, then the acetal protecting group cannot stay. And after the hydrolysis, that carbonyl, ketone carbonyl, can also be reduced.